Okay, so in this video, we're going to take a look at the flight test work for EG203 dynamics. And so what we're going to start with is thinking about the body axis system on an airplane. So the X direction axis is straight out the nose of the aircraft. And it's always out the nose of the aircraft. So these are relative velocity, or relative coordinate frame with respect to the plane. So X is out the nose, Y is out the wing. And so pretty much nothing we do is going to involve the Y axis in this class. And then Z is straight out, basically the bottom of the aircraft. And so if the wings are level, and the fuselage is level, then X is horizontal in the direction of motion, and Z is pointing straight downward with Y pointing out the wing. Now, if this aircraft tilts, and so this aircraft perhaps is climbing, then the X direction axis is still in the direction of motion. It's still out the nose, but Z now, instead of being vertical, may be rotated so that it is somewhat in an inclined position. And so things to know about this is that we have a Cessna 172 airplane. It is outfitted for data collection, and that data collection was originally done by CalSpan. We have a currently modified version because the CalSpan version is a bit outdated, and we call it the MFDRS, and you can see the acronym here. Miniaturized Flight Data Recording System. And this data is recorded in the aircraft and then downloaded to a laptop. And what we'll end up with is an Excel file that looks a bit like this, where the record has a record number. We have a time that the record was taken, a date. This would have been March 21st, 2021, or 21 of March 2021. It's unfortunate that those are the same, and then we have time in 5/100ths of a second, or rather 50 millisecond increments. And we'll go across, we'll see some of these are relevant and some of them aren't. One thing to note about airspeed is relative to the aircraft. So that is a relative velocity, not an absolute velocity. It is the velocity of the wind traveling over the pitot probe. And so if there is in fact wind, the plane might not be going the same ground speed as airspeed. Only in a perfectly still air would the plane's ground speed and airspeed be the same. So something to think about is relative velocity. There's also a GPS receiver, so we have GPS data on the aircraft. The MFDRS looks a little like this in the aircraft. It sits between two of the seats. And what you need to know is that we have 7 records in the data to be analyzed. Record 1 is a static test just to show that all the instrumentation is working. And then 2 through 7 are identified here. And so what we're going to look at is how do kinematics help explain accelerations, airspeeds, and positions? Okay, so when we think about taxi kinematics, so taxi is when an aircraft is on the ground and moving and accelerating, usually. So then what are the relationships between acceleration, velocity, and position? What's the relationship between airspeed and acceleration? Can you determine the ground speed velocity as a result of acceleration? And then which accelerations are relevant? So these are some questions you might ask. In takeoff and landing, which accelerations again are relevant? Can you identify where takeoff or landing happens? And what do the variables look like before and after that event? And then in a 60-degree banked turn, I want you to think about the free body diagram of a plane in a banked turn. And a banked turn is when the wings of the plane make an angle with the horizontal, or the lift of the plane makes an angle to the vertical, and that's a banked turn, what coordinate system would you use? And how does the lift change? Where does z acceleration point? Can we know what the z acceleration is if we know the banked turn angle? Can you see in the data where the turn starts and ends? Does altitude and velocity stay constant? And so what you're going to see as you think about these questions is that we can look at graphical representations of the data and evaluate flight test data knowing our kinematic relationships from dynamics. And so you'll see this guideline, and you should read through this and ask questions. And what I want to encourage you to do is explore in several ways, and you'll see objectives. That part of our objective here is to explore kinematics and use that to understand if the data, the flight test data, makes sense. And part of this is to explore Excel and see if we can visualize or represent data in a visual way effectively. So, for example, when I looked at the longitudinal acceleration in G's, there was a lot of noise in this graph. And so you can see that I have these data points that don't make any sense, and then I have these fairly consistent data points that look like maybe they make more sense. I can see airspeed, right? And so this is the taxi, and I have another taxi data. This is all of my acceleration, which is relevant and which isn't. Why is z direction all just about 1? Why is the y direction all just about 0? And so that's the kind of thing you should be trying to graph and think about and explain. When I look at a bank angle, my z direction acceleration has a pretty steady level here and a drop off at the end. What does that mean? Did it reach a 60-degree bank? These are the kinds of questions you want to think about. And so that's a primer on what you're going to be doing with this flight analysis. More to come.